We are here to solve a very interesting lead code problem, which is minimum number of days to make m bouquets. In this problem, we have been given an array, an integer m and integer k. Now let's understand the problems through some test cases. Now in this first one, we have been given an array which denotes the bloom day or bloom time of each individual flowers. So let's understand the first flower will bloom at the day 1, this one will bloom at the day 10, this one at day 3, and day 10 and day 2. So it has been given the day in which these flowers will bloom, and we need to make three bouquets with flowers size k. That means we need to make three bouquets of each of flower size k. So can we do so? Let's see. In the day 1, we are able to make one bouquet out of this flower. So it is done. In the day 2, we can select this flower to make a bouquet of size 1. And then in the day 3, we can make this flower of size 1. So we are done with the three bouquets within 3 days. So this is the first one. So let's go to the second one. Second one needed to make three bouquets of size 2. So there must be six flowers needed. But we are given five flowers only. So is it possible? No, of course not. So we will return -1. And then in next test case, we have been given this array. We need to make two bouquets of size 3. So let's say, can we do so? Let's say in the day 7, we can make a bouquet. In the day 7, we can make a bouquet of three flowers. So it is possible. Okay, it is possible in the day 7. Okay, now in the day 7, we can see there is this flower and this flower also available. Can we make a bouquet? No, of course not, because in the question it has been said the flowers has to be adjacent. If you look carefully, there is a 12, there is a flower which will bloom at the 12th date. But we are standing in the day 7. In the day 7, this flower is absent. So we cannot make a bouquet of these three flowers, right? So we are unable to do so. So what to do? We have to wait for the day 12 when this flower will bloom, and we will make a bouquet of this, either these three flowers or these three flowers, anything. So we need at least 12 days to satisfy this criteria. So this was the problem statement. So let's understand how can we solve this problem. So one very easy solution that can come into anyone's mind, that since we have been given number of days, we can easily iterate from min days to max days and try to figure out whether the condition can be satisfied with that date. So let's say my min day is 1, my max day is 10. Let's in the first test case, the min day is 1 and max day 10. Let's say we iterate from my day iterates from min to max, right? Now we for every day we try to find out, is it possible to make a bouquet. Now we will create another method. Now this, just let's say this is a black box method. It will just try to figure out whether the bouquet can be achieved. So yeah, is it a possible solution? Yeah, we can arrive at the solution by using this approach. Now the time complexity of this approach will be order of max minus min. It will be order of max minus min, that is it will be of linear time complexity. So can we optimize this approach? Yes, we can optimize this approach, and we can notice a very interesting pattern. We when uh, we we know that our result will always lie between this min to max, right? So for example, let's say our result was 3, right? For this 3, let's say we already know the answer before solving the question, and the result is 3. So we at the day 3, we can we will be able to achieve all the criteria. So and now this 3 will always lie between this min and max. So what kind of approach comes to our mind when you see these type of problems? Generally, it will always be a binary search, right? Because our solution, resultant solution, lies between the two extreme corners. We know the left, we know the right, and our answer will always lie between this one. So it will be always a binary search, right? That's a very easy case. So what can you do? We can have a we need to keep two variables that will keep track of the minimum and the maximum. It will be low and high for us. We'll find the meet for them. That will be the optimal days that for which I need to uh, try for this condition, if it is true or false. Now if this condition holds true, that means by this time, by this day, we are able to fill up all the buckets, right? Now, will there be any better solution available? Of course, it will be better. So we'll try to minimize these days by keeping to the left sub array. Now this statement is very ambiguous, so let's put this up. It will be clear very soon. So let's take a min. It will be max value, and max days it will be min value, because we'll try to figure out the minimum maximum days possible, because it will serve as the two cornerstones for the binary search. So let's traverse this array bloom day and try to figure out the minimum and maximum days. This is the minimum. Day. Let's copy this thing, control C, control V. Oh man, sorry, I have a nasty keyboard. Okay, so we are done with finding the mean and maximum days. Now these are my left and right, left and high. So what we'll do, we will now my solution, my the final solution will always lie between these two extreme days, right? So it will be always mean days less than max days. So now let's the optimal days. Let's say this is the optimal day. Now optimal day will be minimal days plus max days minus min days by 2. That is the mid of this. Let's say the mid of this is the optimal day, right? Now we try to figure out, is it possible to take all buckets, to make all buckets within this optimal day. Let's say it is a monotonic commutative. We'll figure out in the later part. Let's say we are able to complete the all the buckets within this optimal day. So what we'll do, will this be our solution? Will this optimal days will be our result, final answer? Yes, it can be, or it may not be, because in the day four, let's say the answer is 3. Now can we achieve the solution in day 4 or day 5? Yes, of course we can, because if we can arrange all the buckets within day 3, so it is also possible for me to arrange all the buckets in day 4, day 5 as well. So it is also possible. So it will be wise to keep a pointer, to keep a variable that will keep track my base days found so far. Now, once it is done, I will always try to make sure the minimum that we can reach. For example, we found, let's say the optimal days is 5, right? Now, for 5 days, we can obviously arrange all the buckets, right? Now it is my duty to make sure to find whether there is any day lesser than this number day 5 be available. So what to do? I will keep decrementing my highs, right? So what to do? Just yeah. So if let's say we are able to find the optimal answer in the 5 days. So what we'll do, we will keep track the day 5 as a best solution available so far. Now we'll keep on pushing the minimum days, the minimum so far. So we'll try to reduce the maximum days. So we'll try to reduce the right subpart, right? And try to look in the left subpart. So that is what we did so far. Now after this we found our answer that is best. We are now will return this answer. That's very easy. Now let's, yeah, let's initialize. Now let's write this is possible criteria. Now it will be obviously boolean, right? Now for me I need to have lot of argument, not just possible days. I need to have the bloom days, number of k, the number of m also, right? Now this is optimal day. I need to have bloom day. I need to have k. I need to have optimal day. That is very easy. Now let's try to figure out how we can do this. Now let's say optimal day is, let's go to this test case. Let's say the optimal day is 7. Let's say we have counted the optimal day as 7. Now we'll try to figure out within day 7 how many flowers we can pick up. Can you pick up this flower? Yes. Can I pick up this flower? Yes. Can I pick up this flower? Yes. Can I pick up this flower? Yes. So let's take a counter. We'll try to look through this thing. Let's think. Now let's try to find out if this flower can be bloomed within this optimal days. If this is so, if this is so, sorry, we can obviously count it, right? Now, if we cannot, let's say we are here. Let's say the day is 7. We are at this test case. Can we pick up this flower? Of course not. And since we cannot pick up this flower, we can no longer make a bouquet, right? Since in the question it has been stated only the adjacent flowers will be counted. So my approach trial will halt at this place. So I need to make a bouquet out of these all 4 flowers. So what to do? I will find out the bouquet that we can make at this juncture. Now the number of flowers, that is 4. Now there must be 3 flowers available. So 4 by 3 1. That means out of 4 flowers we can make one bouquet of 3 flowers, right? That is 4 by 3. One bouquet can be made possible with 3 flowers. That is count by k, right? Now this is important. Don't forget to uh, reset the count value to 0, because because my the counter will once we are at a odd flower index, my counter will reset to 0 and will again reset our journey, proceed our journey with new counter. So it is very must. So let's, now we have found this bouquet, right? Let's say, now this is very important also. Now we have found one bouquet for up till this position. I mean the count is 1, and now we'll keep on iterating this position also, right? This position also. So can we count these flowers? Of course we will. So it will be 2. Now it is my duty. Now the my loop will end at this position. Now the count is 2. We have finished executing. Now it is my duty to know whether the residual count that is done at the end to justify whether I am make a bouquet of size 3. So what to do? Let's say the count is now 2. For example, at this position the count was 0, and after iterating through these sevens, the count became 2. Now I would try to know, can we make another bouquet of size k? Can we? 2 by 3 it is 0. No, we cannot, because there are only two flowers. We cannot make a bouquet of size 3, so it will give me 0. So let's return whether this bouquet is greater than equals to the number of bouquets that you needed to make. If this is true, then return true, then it is possible to do so. If this is not, then it is not, right? This was the thing. This was the thing. Let's initialize this. Okay, let's try to run. There will be typos for sure. Yeah, max days, man. Okay, there are max days. We have some problem. Why it is so? Why it is so? uh, why it is so? It is saying that I haven't found any solution. So why it is so? Let's understand this thing. I did make some mistake, like as usual. Optimal less, this is the mean, max minus mean by 2. Best is the optimal one. If it is possible, then just reduce this thing. And if it is not, then increase the number of days. It is very also important. And integer dot min max value, minimum days, integer dot min value, minimum days is, sorry, yeah, yeah. So we are succeeded. Now let's understand the time complexity of this problem. The time complexity of this problem, we are looping from min to max days. So it will be obviously max minus min into, it will the this problem. Now this problem, let's say it is, we now this now this is taking logarithmic approach, but this one taking order of n, right? Because we are looping through this entire bloom day, sorry, we are looping through this entire bloom day array. So it will be, let's say n is the length of the day, length of the bloom day. So it will be n cross log of max days minus min days, because this operation is taking log operations. And for every operation we are invoking this function call, that is possible. And is possible is taking order of n days, that is bloom order of bloom day dot length. So it will be order of n class. It is our time complexity. And the space complexity would be very simple, that is order of 1, because we haven't taken any extra space. Yeah, that is it. So it was a very not a very unique problem, but just like aggressive crows and Pratas just like other binary searches. And that is it from me. Thank you.